Okay, I think we're going to be ready to roll here for lecture 4.7. Notice that we skipped 4.6. That is certainly okay. But what we'll do now is talk about these types of chemical reactions. Okay? Sorry, it's been a little while since I've done one of these, especially in the basement. I've got new surroundings to get used to. Okay, so as we can see, the types of chemical reactions in the happy days, we had synthesis, decomposition, oxidation, reduction reactions. So some of these we've done before, but AP Chemistry kind of groups them a little differently. All right, and I am really frightened down here. I'm just telling you guys that. If I don't make it out, it has been really a pleasure. We're gonna. That's coming from behind that door. All right. So we're going to group the first one as a precipitation reaction, and you probably remember doing some labs. We called it a PPT, a precipitate that was forming in the solutions. So what happens is you have these ions floating around in water. And there's something about their nature that makes them want to form a solid even in the presence of water. So they overcome that property of water that usually keeps those ions separate, and they overcome that and they form a solid. So in order for this type of reaction to occur, you have to have an insoluble salt. Now, there are some really good rules that they use for AP Chemistry. I'm going to let you cheat a little bit before the exam and use the back side of your yellow sheet. It has solubility rules. And on that side, we talk mainly about the cations, and we say all nitrates are soluble. All ammonium compounds are soluble. And anything with these positive cations, sodium or potassium, you know they're going to stay an ion. Okay? So in other words, sodium's not going to pair up with anything to form a solid while it's in water. You know, obviously sodium can form a solid, sodium chloride, which we use all the time. But when it's in water, I challenge you to get it to crystallize within the water. That does not occur. All right, so it's not like making those sugar crystals that you can tie a string in there and it starts to crystallize. These will always remain in the aqueous form. All right, so that gets us started with something like this, like write a balanced complete ionic and then a net ionic equation for the reaction that takes place. I actually showed you a little bit of the yellow precipitate that formed. So we have kind of introduced this earlier on, but now we're going to get a little bit more in depth. Last year, we would have kind of provided this sort of double replacement reaction. We're going to call them precipitate reactions right now, because the term double displacement is a little bit misleading. As you have learned, that there is sort of a way of talking about what the real business part of a reaction is. So the reality is we write it like this, but this is not a structural unit all in of itself. If it's aqueous, that means there's a lead plus 2 ions and there's 2 NO3 ions. and there's one sodium ion and one iodide ion, and they're just floating around in solution, all surrounded by water molecules. That's what aqueous means. Well, when we react those, the lead and the iodine, they combine together. They used to use lead in paint. I'm sure the wall behind me is covered in lead. Another good reason to be down here. So lead iodide, it will form a solid, and that's why it made really good paint, because it's insoluble. You could make like a nice water-based paint, and that yellow solid would come out of the solution and make a nice paint. So this particular one is yellow in color. And then over here, you got the same situation going on where it's just ions in solution. So if this was also aqueous, then nothing happened. Nothing changed. You got ions in solution, ions in solution. So it is important that you find an insoluble salt, in this case PbI2, lead 2 iodide, that forms a part of the reaction. Now, one of the things you learned in the early part of chapter 4, some of you be a little rusty, about 8 of you that had me first quarter, be a little bit rusty on this stuff, so you might want to go back and look over that net ionic equation, but we are certainly going to get a good review here on it. You can see, does the lead change? Yes, it does. Does the nitrate change? No, it doesn't. One of the things that changes on it is you're like, whoops, we accidentally destroyed matter. So you're going to look and you go, well, we got to balance that equation. So you can balance it, and this is a little trick when you do these with polyatomic ions. Just keep them together and say there's 2 NO3s over there, and now there's 2 NO3s over there. Makes the balancing a little easier. So you can see that the lead changes, the nitrate doesn't, and the sodium doesn't. So guess what? We're going to leave the Na and the NO3. Those were the two that we said sort of form always soluble compounds. So they are never going to be part of the equation. So now we rewrite and we talk about the net ionic equation. So this is a little bit tricky, so make sure that 2 still remains there. You don't want to change that to I2, because that's not the reality of what is happening right there. So you don't want to put the 2 behind it and make solid iodine, which certainly doesn't occur. So it's 2 iodide ions that's occurring. So just that one lead, 2 of those iodides, and then the sodium and nitrate are gone. They are spectator ions. You get rid of them. Okay? So make sure you pause and get that down nice and clear. And we're going to check. And by the way, you can use your yellow sheet backside to prove that lead compounds are insoluble, or certainly PbI2 is, and many lead compounds are. Okay, now on this next slide, it's the same concept. So we'll go through it a little faster, but I want you to try this one on your own. So go ahead and hit the pause, and I'll just wait for you in the cellar. Hit the pause. Okay, how'd you do? How'd you do? Well, let's take a look. You were asked to write the complete ionic equation, and if that is asked of you, you're going to have to do that to get the points. So you do this old school. You do this like you would have done this problem last year. You take your yellow sheet out, you write the correct formulas, and you say it's going to do the double switcheroo. The calcium's going to go with the carbonate, the sodium's going to go with the nitrate. Now, my guess is some of you may have made a mistake, and kept those parentheses around that guy. That's why it's really important you try these. Get rid of some of those old habits. Remember, sodium is +1, nitrates -1. There's no reason to use parentheses or anything complicated there. And then the calcium, it only needs one of them because that's +1 and that's -2. So hopefully you caught that. And certainly that's not balanced, but you're going to balance it that way. And that's how you make the 2 of each of those guys, which we know are not important. So when we write the net ionic equation, we get rid of them. Sorry, you are insignificant. Nitrate and sodium go away in the net ionic equation. And when asked to write chemical equations, you should assume that they're talking about the net ionic equation in organic or in AP chemistry. They're really big on that, and that's super important. Okay, so that right there is the correct answer, and carbonates are mostly insoluble, and certainly you can find the rule on your yellow sheet that confirms that there's a solid. Now, if this is a precipitation reaction, obviously you're going to have to assume that there's a precipitate, and a precipitate is a solid. So that is part of what we got here. Is this balanced in that form? Yeah, absolutely, because it's just one of those, and one of those makes that. So hopefully you did okay with writing that, and of course you'll get a chance to practice some more in the problems. All right, now the rest of these reactions, and this is just an introduction today, are going to be this oxidation reduction. Okay, that's a give and take. There are many reactions. As a matter of fact, the majority of chemical reactions, there is an exchange of electrons. You shouldn't be surprised by that. That is sort of what makes something reactive or not reactive, is how many electrons are in the valence shells. So this idea, this give and take, there's a losing and a gaining of electrons, is oxidation reduction. Now, oxidized loses electrons. Remember Leo. Leo the lion, lose electrons, oxidation. Gain electrons, reduction. Grrr. That's what the lion says. Grrr. And that GER will get you on the right track. Okay, so going to an equation like this. This will seem a little strange to you without all the ions in it, but this is not the same thing that we talked about, because those ions just stayed ions and stuck together. But what happened here is you had a solid that became an ion, and you had an ion that became a solid. Well, if you look at this, let's start down here with our good friend Leo, and you can see the oxidation number goes up. I always think of the lion jumping in a little pink tutu, and he's jumping up in the air. That image reminds me that if that number goes up, that's oxidation, because the lion is going up. Now forget about gravity coming back down. That's the sad part. So think of him happy and jumping. So up the lion goes. As the number goes up, that's Leo. That's oxidation. Now, here the oxidation number went from +2 to 0. That is a reduction in the number, and it's reducing. So that's your GER. And that's how we're going to look at these reactions. I'm just about end of the recording time, and I just need to go for a walk and get out of the basement for a little bit. So next video. Bye.